Hearty welcome, dear students, to the next series of Gurukul lectures. Today, we begin where we left off the last time in digital systems and applications. We had begun to discuss the basic memory element in digital electronics, and which were the flip-flops. Flip-flops, as we saw last time, are a circuit which are used to store a binary number and whose output will remain unchanged once set, even if there is a change in the input. Hence, flip-flops are understood to be a bistable electronic circuit having two stable states, where the output in analog terms can either be 0 or 5 volt, while in digital terms it can be 0 or 1. They serve as a memory because until and unless we make an intentional change, they retain the last state. The last state could be a 0 or a 1, and hence the flip-flop behaves as a memory device. So we saw that the easiest way to construct a flip-flop was using two NOT gates, and then the basic flip-flop, or rather a latch, was the RS latch. The moment we gave it clock signal, it converted itself into the flip-flop. The basic idea here was the feedback. The output of the top flip-flop was one of the inputs of the lower NOR gate in this case, whereas the output of the lower NOR gate was one of the inputs of the top NOR gate. This way, we could actually have feedback to both the NOR gates. We understood how the RS flip-flop worked, and we saw that it could be realized using either NOR gates or NAND gates. Why the preference for NOR gates and NAND gates? That also we have discussed previously, since these two gates are universal gates. We prefer the NAND gate because in this part of study we concentrate on sum of product solutions. With NOR gates we get product of sum solutions. So in NAND gates we found that the truth table for the RS flip-flop served as follows. Since there are two inputs, R and S, hence as per digital logic it should have four combinations: 0 0, 0 1, 1 0 and 1 1. What we noted in our class was when S and R both were 0 0, then output of the SR flip-flop was retained in the last state. That is, whatever state was stored in the SR flip-flop during its last occurrence got or was retained in it. When S became 1 and R became 0, that is 0 1 combination, we found that the output of the truth table got stuck at 0. When S became 1, R became 0, then the output was fixed at 1. When the case, as we tried, as S equal to 1 and R equal to 1, then the output state of the flip-flop was a forbidden, because both Q and Q bar returned the same values, which are not allowed in digital electronics. Q and Q complement or Q bar should always be opposite to one another. Hence, we inferred that S equal to 1, R equal to 1 state was not allowed in SR flip-flop. So we realized the SR flip-flop using NAND gates only. In this diagram, as you can see, that we have a latch, and behind the latch we have two more gates, and the truth table is summarized again: 0 0 last state, 0 1. In this case R and S are switched, so we can see that R is equal to 0, S equal to 1 is 1, R equal to 1, S equal to 0 is 0, and 1 1 state is forbidden. Now the problem is that with two inputs, we are not allowed to use one particular combination. In this case, S equal to R equal to 1. Now this reduces the data carrying capacity of our flip-flop, and hence more efforts were made to redesign this SR flip-flop so that even the combination S equal to 1 equal to R was allowed. That we will see over the next couple of slides. So we also understood that clocked RS flip-flop was the NAND or NOR realization of the RS flip-flop. And also this SR or RS flip-flop are called transparent because any change in information at R or the S input is immediately transmitted to the output Q and Q bar. Addition of the two AND gates at the R and S input are shown, and they will allow us, as we will see, they allow us to use the flip-flop enabled condition or disabled condition. The figure here shows the use of two extra AND gates, and we understand that what is the logic of the AND gate of any number of inputs, okay, gives a high output if and only if all of its inputs are high. So it is pretty clear from this picture that till the time this enable or the clock is high, only then will the inputs S and R flow into the AND gates and come at its output. Otherwise, the moment enable is 0 or clock is low, at that time, irrespective of the values or the combination of S and R, the output of the two AND gates will be 0, 0. And for the RS flip-flop, the output Q and Q bar will be fixed at the last state. Of course, Q and Q bar will be complement of one another. Hence, the symbol of this clocked RS flip-flop is shown over here. Now this clock is also known as the trigger. This clock triggering of the flip-flop can be of two types. One could be the level triggering, and in order to make the flip-flop work faster, we also sometimes prefer the edge triggering. So edge triggering simply means that it could be a rising edge, that is going from 0 to 1, or a falling edge, that is coming from 1 to 0. Level triggering, on the other hand, implies that the clock will either be high or the clock will be low. So looking at the truth table here, we see that till the time the clock is 0, the input combinations of S and R do not matter, or in the parlance of digital electronics, we can say that is don't care. That's why we have put two X's over there. So till the time clock is 0, R and S can be XX, and Qn plus 1 will be the last state, that is Qn. The moment clock goes 1, then all the four combinations of S and R are allowed to pass, and the flip-flop behaves as defined in the earlier truth table. That is, for 0, 0 with clock 1, with 0, 0, it is the last state. For R equal to 1, S equal to 0, next state will be 0. For R equal to 0, S equal to 1, the next state will be 1, and the moment S and R both go 1, that state is forbidden. So the same thing happens when we have the clock as enable. Till the time enable is 0, nothing changes. The last state is always retained by the flip-flop, and the moment enable goes 1, the information at R and S inputs are transmitted directly to the output. Moving forward, we had seen that this picture here shows the clocked RS flip-flop using NAND gates only, and the clocked RS flip-flop using NOR gates only. So NAND realization and NOR realization. So we consider one special application of SR flip-flop. In this case, if we look carefully, then for the values S and R being 0, 0, the last state is retained, and when the case somehow arises as S equal to 1 and R equal to 1, then that level is forbidden. So effectively, the flip-flop is having or processing data only during two states when both the inputs S and R are not equal to each other. In this case, we assume that the enable is on, that is, or the clock is high. So D flip-flop needs only a single data input. If we look carefully, we see that there is a modification which with the D input, wherein we can see that S and R can never ever have the same value. If we look at the circuit, we see that for one of the AND gates, the D input is fed directly, whereas at the same time the other AND gate has a NOT gate from the D input in between. So if the value of D is 0, then it is fed directly. An upper AND gate will give a value of 0, whereas the lower AND gate will give the value output as 1. In this case, we assume that both the clock or the enable is at high state. So looking at the truth table, we see that the clock, till the time the clock is 0, again the value of D goes to don't care, and irrespective whether its value is 0 or 1, the last state is output from the D latch. When clock is 1 or enable is high, then if the value of D is 0, then the next state output from the D latch or the D flip-flop is 0. If D is 1, the output is 1. So this way we can actually see storage of a word, which in digital terminology are 4 bits together in a flip-flop. So as we can see that we have 4 D flip-flops, and the D flip-flops have all their clocks connected with one another and also to the main circuit with the clock input. So that simply says that all the D flip-flops will be working at the same point of time when clock is high. So initially what we do, we make the output of the 4 D flip-flops as 0, and hence we have Q3, Q2, Q1 and Q0 as equal to 0, 0, 0, 0. Now if we, after making them 0, 0, 0, 0, that is Q3, Q2, Q1, Q0 all as zeros, we make the clock 0. Now these 4 bits are stored in the D flip-flop, or at the 4 bits till the time we want to make a change. When we have a new data input, when D3, D2, D1, D0 happen to have a new data input, then we again energize the clock and feed in the data. Hence, in this case, the clock actually helps us enable or disable the storage. In this case, suppose we want to input 1010, that is D3, D2, D1 and D0 equal 1010. Then as soon as the input is available at the D inputs of all the flip-flops, in this case 4, then we make the clock go high. The moment the clock goes high, the data from the D inputs is available as output at the Q. That is, with the first clock pulse being switched on, we will have D3 going to Q3, D2 going to Q2, D1 going to Q1 and D0 going to Q0, and then the clock is removed. So initially, with the first clock pulse, when we reset this word, that is the 4 D flip-flops, the output Q3, Q2, Q1 and Q0 were 0, 0, 0, 0, and the moment we switched on the clock and the data flowed into the D flip-flops, the output now changes to Q3, Q2, Q1, Q0 as 1, 0, 1, 0. We remove the clock and again, or make the clock 0, and again the output of the 4 D flip-flops gets fixed as Q3, Q2, Q1, Q0 as 1, 0, 1, 0. Now, even if the inputs D3, D2, D1, D0 change, then the output would still be 1, 0, 1, 0. This implies that this set of D flip-flops behave as a 4-bit memory element, and there is no change in the memory till the time we do not switch on the clock and allow the input data to pass to the output. Suppose the input now changes to 0, 0, 1, 1, that is D3 is 0, D2 is 0, D1 is 1 and D0 is 1. Then again we make the clock go high, and Q3, Q2, Q1, Q0, which was earlier 1, 0, 1, 0, now changes to 0, 0, 1, 1. And this means that whatever input was available at that point of time in the 4 D flip-flops, they were allowed to pass on to the output because the clock was high. After this again, if we set the clock at 0, then we get the output fixed as Q3, Q2, Q1, Q0 as 0, 0, 1, 1. So in this way, we have taken 3 examples initially, how we put or have initial, when we clear data, we have the output as Q3, Q2, Q1, Q0 as 0, 0, 0, 0. After that, we discussed how the input D3, D2, D1, D0 being 1, 0, 1, 0, and how is it transferred to the output Q3, Q2, Q1, Q0 becomes 1, 0, 1, 0. And in the last case, we had the inputs 0, 0, 1, 1, and again we set the clock high and we find that Q3, Q2, Q1, Q0 came out to be equal to 0, 0, 1, 0. So initially, we also see the same kind of thing in a calculator. We have a button called all clear. It is AC written over there. So all clear cleans out the memory and it resets it to 0, 0, 0, 0. In this case, there were 4 D flip-flops, so we could process only 4 bits. Now students, we can actually imagine that when we download movies which are at the minimum around 700 MB odd, I'm talking about very low resolutions, right? With a fast internet speed, we download much more. So we can understand that what is the requirement of the hardware that happens in these digital circuits, be it our mobile phones or our laptops or even our direct to home transmissions coming directly from the satellite to our homes. So actually we can see that when we have gigabytes of data, then how many flip-flops are required to process each and every bit. So digital electronics is very important to understand the lifestyle that we enjoy nowadays. With 5G coming in, we would still have more and more data being processed at a higher and higher speed. So thanks to all these engineers and scientists who have made this possible, as also our device engineers who have made the devices to be as small as possible, yet we have increased the processing speed. So the D flip-flop in this case that we were discussing for storing the 4-bit word has the following characteristics. In this case, when the clock goes high, the input data is loaded onto the flip-flops and they appears at the output. When the clock goes low, the output retains the data, and this data is retained till the time the clock goes high at the next instance. So we consider another example as D3, D2, D1, D0 as 0111. So hence, when the clock goes high, our output, that is Q3, Q2, Q1, Q0, would read as 0111. So as long as the clock is low, the D values can change without affecting the Q values. That simply means that the Q values are at the output, and hence they do not change even if the input, which are the D values, they change when the clock is low. And hence we find that the D flip-flop behaves as a very nice memory element. Now we go for what is known as the edge triggering. Edge triggering is required because we need more and more data processing, and that too at a faster speed. We have all played our video games or computer games, and we find that they have lot of graphics involved. All this graphics is a bit of data that is being processed. So we just take a break, and after this we'll just come back and discuss the edge triggering and how it actually quickens the data processing in digital circuits. Thank you.